It is a pleasure to introduce Professor Arpita. I'll just read out her introduction, which should give you a kind of some motivation in terms of what all you could pursue as a student as well as a faculty. Dr. Arpita Mondal works as an associate professor in civil engineering and the Center for Climate Studies at IIT Bombay. Arpita has been a researcher, educator, communicator in climate change with more than 15 years of experience. Arpita's research focuses on hydroclimatic extremes such as heat waves, floods, and droughts, how they can be characterized, what causes them, and how they are likely to evolve with climate change. She serves as an associate editor of Earth's Future, Journal of Hydrology and Hydrological Sciences Journal. She has been featured in the book She Is 75 Indian Women in STEAM. That was the title given by the Office of Principal Scientific Advisor to the Government of India and Red Dot Foundation. Arpita received the Asian University Alliance's Scholars Award in 2020, DST's Inspire Faculty Award in 2020, SERB's Early Career Research Award in 2020, and the SERB's Power Research Award in 2023. Okay, Arpita completed her PhD in civil engineering at the IISc Bangalore. When she had received an Endeavour Research Fellowship of the Government of Australia, the Fulbright Nehru Research Fellowship of the United States India Educational Forum, and the Berkner Travel Grant of the AGU. Along with publishing in peer-reviewed scientific literature, Arpita strongly engages in public media outreach and has been a regular author and featured in print and television international media. With this, I thank Arpita for joining today, also being that inspiration in terms of the achievements. Over to you. Thanks.
I should shorten my bio. Lesson learned. It's way too long. So as Vishal said, my name is Arpita and I work for the Department of Civil Engineering and also Climate Studies at IIT Bombay. So at the outset, I must acknowledge my 3 PhD students. So Manish Dasmana, who's graduated and works for a company which works on the insurance risk sector in Bangalore. Mariam, who was the first PhD student to graduate from my group, she's postdocing at Imperial right now. And Roshan, he has also submitted his thesis and gone off to the UK to St. Andrews. And also, I would like to acknowledge the World Weather Attribution team, which is actually a team of global experts, but led by Imperial College London. We must acknowledge, as is the trend nowadays, to acknowledge First Nations people. I don't really know who the First Nations humans of the place Powai, where IIT Bombay is located, are. But I do know the non-humans there, and some of them are depicted in this picture. So we not only have lots of birds, which are, many of them are actually migratory, but also predators like the crocodile, which is in the Powai Lake, and here is this Indian rock python, which graced our parking lot a few months ago. So a little bit about what I do. I use a combination of statistics and physics to understand how extreme events such as floods, heat waves, and droughts can be defined, what causes changes in them, and how they are likely to evolve in a world of global warming. So here you can see images of, for example, heat waves. We see the tarmac of Delhi roads of 2015 having melted, floods of Chennai, droughts in 2000, where the Krishnarajasagar Dam in Mysore almost ran dry. And we try to understand how they are likely to evolve with climate change. So I'm sure many of you know these stripes. So these are called the global warming stripes, and this was actually originally proposed by a Professor Ed Hawkins of, I think, University of Reading. So each stripe represents temperature of each year across the years of measurement. The blues represent cooler climate, reds represent warmer climate. This is the global average temperature. And we see that in the last 20, 30 odd years, there is barely any blue line. Everything is red, which basically means that we have warmed the earth. Now, there are many visual representations of climate change, and this became one of the more popular ones, which were later adopted in not only cafes and buses and football jerseys, but also in this movie. This is an interesting movie. If you haven't watched it, I mean, I also haven't watched it. I don't know where I can get this though. So here in the poster of the movie also you can see the stripes, and there was a hashtag which trended for some time called "Show Your Stripes." And Ed Hawkins' website also has a portal where you can, for your own city or your own place, you can check how the stripes of that region might also look like. Okay, so considering I suppose most of you are PhD students or postdocs, and considering the different backgrounds, especially I heard someone from the Center for Artificial Intelligence, and I can see some of our own PhD students, but so pardon and bear with me if this is repetitive to you, but I'm going to start with the basics so that all of us are on the same page. So weather and climate are not the same thing. Weather is what happens over a much shorter time scale, day-to-day scale. Climate is averaged over a longer period of time. So, and as they say, climate is what you expect, weather is what you get. So then the natural question to ask is, how would climate change affect weather, and can it really affect weather? So I think by now all of us are convinced that the earth is warming and human emissions of CO2 and other greenhouse gases are responsible for it. I hope we agree all of that. Is there anybody who's a big fan of Donald Trump? You're pointing fingers at someone. Is there someone like that? Okay.
Yesterday, there was, during Professor Raghu Muttugudde's talk, he asked the same question, and like one person refused to raise their hand and said that they're open to debate. So this is the reference to that thing.
All right. So, this reminds me, there is a climate scientist called Kate Marvell. So she has given a very nice TED talk also on the science of climate change. But she said, her father has been, which is the more conservative party? The Republicans, right? So her father was a staunch Republican, and he was a big time climate denier, despite the fact that she was such a renowned climate scientist. And you know what? In an interview, I heard her say how her father's belief changed. And it has got nothing to do with the fact that his daughter became the champion of the cause of climate change. But what changed him was a very capitalistic perspectives of how insurance prices across the US are changing. So US is a very capitalistic, I hope nobody is recording me. The US is a very capitalistic society, and they understand where there is profit and where there is loss. And the market shows belief in climate change. The market shows exaggeration of extreme weather. So even if you do not believe in the science of it, the economics should actually make you believe. Anyhow, with that, I don't know if I'm able to convince you, but we are going to go ahead with the assumption that all of us believe that human-induced greenhouse gases have caused climate change. So what we do have here is the data, observed data of temperatures across the globe. And if you see 2024, the number of hottest days on record is just this humongous amount of reds that you see vis-a-vis other years. So every year is overtaking the previous year to be the hottest year on record, right? Now, how does this affect extreme weather? As I said, weather and climate are not the same, but when the climate changes, there are physically based reasoning and physical justification and scientific understanding on how it can affect extreme weather. Here is a pictorial demonstration of the different processes which can be affected because of climate change and how it leads to extreme rainfall. But I'm going to focus on two classes of events in this talk. One of them is heat waves, the other is floods. So let us understand how they are likely to change because of climate change. Now, firstly, higher temperatures. So if the average temperature, if the global mean temperatures are increasing, then what happens is the distribution kind of shifts. So your normal becomes, so what used to be extreme now becomes the new normal. When the entire distribution shifts, the probabilities of events in the extreme tails basically increases. So you have more chances of heat waves happening. So this is sort of the physical justification as to how extreme temperatures are likely to increase with climate change. Now, when we come to increasing heavy rainfall events and floods, there is a physically based law which is called the Clausius-Clapeyron equation, which tells us that for every degree Celsius rise in temperature, there is 6 to 7% more moisture holding capacity of the atmosphere. So warmer atmosphere can hold more moisture, it keeps holding till it cannot hold anymore, and it behaves like a sponge. Then what happens when you squeeze a sponge is you get a lot of water. So when it rains, it pours. So with these physical justifications, what we do see across, there is scientific consensus. So the IPCC, which is, I'm sure all of us know, all of us have heard about IPCC, right? So the IPCC every 5 years bring out a synthesis report. They don't do any science, they only synthesize what scientists report, right? So they have synthesized, and we see that across the globe, temperature extremes are increasing. So the red color is for increases, blue is for decrease. There is no blue here. And the dots, the number of dots denote the amount of confidence. So for the South Asian region, which is where India is located, we see 3 dots, very high confidence in this understanding that temperature extremes in South Asia has been intensified because of climate change. And so this is one plot from one of our earlier works where we looked at the observed temperature data from the India Met Department. And we see that there are rises in temperature, especially in this north central part of India, which has been reported by other studies also as hotspots of heat waves. However, when it comes to rainfall, as we know, rainfall is a variable which has inherently a lot more variability than temperature. Both spatially and temporally. In fact, in India, you can see average rainfall as high as 2000 millimeters per year to 50 millimeters, to as low as 50 millimeters per year. And also we have a seasonal cycle. So there are inherent variabilities, there are uncertainties. So even though there is increase, and more or less, across the Eurasian region, there are reported increases in extreme rainfall. However, what we see here is, especially for the South Asian region, the confidence is low to medium. So low to medium confidence on an average in terms of the understanding that extreme rainfall event has been intensified by climate change. In fact, if you plot the trends of total extreme rainfall volume, I'll soon come to the definition of how we define extremes. But if you look at the total volume of rainfall, which is above a certain threshold, we see that the trends are mixed. We have positive trends, but we also have negative trends. And this is from Roxy's work, where he and his co-authors basically show that even though average precipitation might be decreasing, the extreme events might rise. So now I'm going to talk about, whenever you have an extreme event, there is a general interest in the public, in the governments, in the media as to, is this event because of climate change? And remember, I said I'm going to talk about 2 classes of events, heat waves and floods. So many heat wave events are in fact found to be attributable to climate change. In fact, India suffered from major heat waves in 2022, 2023, both the years, and 2022 event was particularly anomalous because, not just anomalous, but also impactful, because simultaneously a lot of the spatial extent of the country was under heat wave. It also occurred much earlier. So March, April is typically not the heat wave season in India. May and June are our hottest months, but the heat wave happened around March and April. And not just that, it also coincided with the harvesting season of wheat, which is the second largest food crop in India. And between rice and wheat, between paddy and wheat is the crop which is more sensitive to temperature changes. There are studies which show that above a threshold temperature of 33 degrees Celsius, senescence of wheat happens, which is basically the crop ages faster, right? So what happened because of that is the yield of wheat reduced, and India was forced to stop all the export of wheat. This also coincided with the Russia-Ukraine war, and it had effects on global food chain supply. So this is an example of how extremes can cascade, right? And we were part of this world weather attribution study where we show that so the 2022 event was made at least 30 times more likely because of anthropogenic climate change. Similar kind of analysis was also done for the 2023 event, and again we reported that this event is made 30 times more likely. Now, how do we make these conclusions? This is what I'm going to talk about in today's talk. However, when it comes to heavy rain events, not all heavy rain events, if you look at attribution literature over the last 15-20 years, not all heavy rain events have shown decipherable signs of anthropogenic climate change. However, two events which did show such signs are the landslide-inducing heavy rainfall event in Kerala and also the floods in Nepal, right? And for both these events, what we report is that the event was intensified 10% more. Like whatever rainfall amount would have been received in a world without climate change, now with climate change, we are receiving 10% more rainfall, right? So how do we come to these conclusions? For this, there is a branch, I can now call it a branch of climate science, which is called climate change attribution science. And it's a fairly new branch of climate science. It started with this phenomenal letter in the journal Nature in 2003 by Professor Miles Allen of Oxford University, where he posed this question, will it ever be possible to sue anyone for climate change? And so till then, as I was mentioning to you, weather and climate were thought to be two different things, and it was believed that you will never be able to tell with certainty whether a particular extreme event has been caused by climate change. But then Professor Miles Allen said, maybe it's an ill-posed question. We can repose the question as to what role climate change has played in making this event more or less likely. And the idea there is actually borrowed from the field of epidemiology. Let us say a person has been detected lung cancer, okay? We will never know whether the person would not have gotten lung cancer if he or she was not a smoker, right? We'll never be able to tell with certainty. However, statistically speaking, we know that smoking increases the chances of having lung cancer. So that's how we are trying to address this question here, that the weather is a random variable. Weather is like rolling a dice. But with climate change, what happens is you're making that dice loaded. The chances of certain faces appearing becomes higher, okay? So now because of climate change, the weather is behaving like a loaded dice. And typically so how do we understand whether the event has been made more likely or less likely because of climate change? Typically conclusions will be like this. Climate change did not alter the likelihood, virtually certain that this event would not have happened if there was no climate change, and exceptionally less likely that this event is because of climate change. You can have a variety of conclusions like this, but how do we make this conclusion? And for this, we need to understand how the world would have behaved if there was no climate change. And for this, of course, we use a time machine. We go back in time, we change the Earth's composition and see how the Earth behaves. And in fact, we are now in a virtual universe. That's not what it is. We have to rely on model simulations. Because we do not have a time machine, we cannot go back. We rely on computers to do the job for us. So these climate models, which Professor Dr. Mukhopadhyay also talked about, these climate models are used to understand how the world would have behaved with human-induced climate change, without human-induced climate change. So we have a counterfactual world, which is without climate change, and a factual world, which is with climate change. And then we look at the probability of this event, the one that we are interested in these two worlds, okay? Why is it important? I don't know if you had followed this news. So there was, in 2024, there was this landmark victory of a group of elderly Swiss women who followed a lawsuit against the government, and they said that they have a right to live in a world, they have the human right to live in a world free of the ill effects of climate change. And they won the case. So the verdict was given based on the scientific attribution analysis that the heat wave event that they suffered from was actually intensified because of human-induced climate change. And roughly around the same time, the Indian Supreme Court had also, this was a filed lawsuit, but the Indian Supreme Court, suo motu, it's like on its own, it gave a directive to the government that you have to give your citizens the right to live in an environment which is free of unrightful stresses, and climate change being one of them. But the Indian government rule also included environmental issues, which we are not going to talk about. And also the other place where this has implications is the Conference of Parties, which is what, so this is a United Nations negotiation platform where all governments come together to discuss how they are going to deal with the problem of climate change. This happens every year. So in the 26th COP, which I'm sure all of you would have heard of the Paris Agreement. So that was the COP which was held in Paris. The COP which was held in Dubai, which is the 26th COP, there, you know, this loss and damage fund was pledged. What is this loss and damage fund? It sort of is giving an agreement that there are, for example, small nations, countries, small island nations whose contribution to global warming has been very little, but they are very vulnerable to the ill effects of climate change. So if they are suffering from the damage of climate change, who's going to pay for them? And the idea overall is that whoever has been the largest contributor should pay for it. So the government sort of came together. So this is a fund which has been pledged. But there are many, many challenges in how you implement them. And so far, it is still at the pledge stage. Okay, it has not gone into the implementation stage. But based on what would you decide who pays who? Based on what do you decide whether the event is caused by climate change or not? That's where the attribution science comes into picture. So I'm going to talk about first some statistical techniques for doing this attribution, and later on I'm going to talk a little bit about some unsupervised machine learning techniques as well. So how this, as I was mentioning to you, we look at the probability of this event. So suppose, so this is the variable, this is the probability density, call it normalized likelihood. Now we look at let's say I'm looking at the rainfall in Kerala, 2024, landslide inducing rainfall, right? I'm going to look at the magnitude of that rainfall and then look at what is the probability of this event in a natural world. So the counterfactual world, that probability distribution is given by this green PDF, and the red PDF shows the probability distribution of events in the actual world. And I'm going to look at the magnitude of that event and see what was the probability of that event in the natural world vis-a-vis the actual world. So P naught by P0 is what is used here, and we obtain what is, so P naught by P0 is called the probability ratio, and 1 minus P naught by P0 is called the fractional attributable risk. So if you, let's say, what used to be a 1 in 10 year event, what used to be a 1 in 20 year event is now a 1 in 10 year event. In a world without climate change, it used to be a 1 in 20 year event. Now it is a 1 in 10 year event. It has become more frequent, right? Then the fractional attributable risk would be 0.5. So similarly, what in the early 1900s, if an event was as rare as once in 50 years, today it has become once in 30 years. So this is how we look at, so these are called return periods, which are basically average recurrence time. So that, what is a return? Let's say I'm talking about floods. What is the 100-year flood? The 100-year flood is that magnitude of the flood which happens on an average, and then on an average term I want to underline, on an average it happens every 100 years. It does not mean that if today you had 100-year flood, next year you cannot have it. Next year also you can have it with the probability of 1 upon 100. I'll explain what this means. So what happens is, let's say you have a weather variable, which is a random variable, and that's an assumption we are going to make. That is a philosophically questionable assumption. You know, because rainfall happens because of physics, right? There are clouds forming, there are conservation of mass, momentum, energy, etc. are satisfied for rainfall to happen. Yet, the variable itself can be treated as a random variable, and you can fit whatever statistical model by statistical model I mean statistical distribution that you want to fit. So suppose a weather variable is a random variable. This assumption has served humanity reasonably well for the last 200 years. All the civil engineering design that you see are based on the assumption that you can treat the variables as a random variable, and hence you can estimate what would be the design magnitude. It has served as a great tool so far. So fundamentally, it is not wrong. It might be, okay, a physicist might disagree with the statement, but engineers are not physicists, with due respect. So here, I am always reminded of this joke, which is you ask different sets of people what is 2 plus 2, and you go and ask the physicist first, and the physicist will say, oh, it is 3.99999. And then you go to a computer scientist, a logician. Hey, what is 2 plus 2? The logician will tell you, define 2, define plus. Then you go to an MBA guy and say, hey, what is 2 plus 2? And the MBA guy will ask you, I'll tell you, but what do I get in return? Finally, you go to the most practical person, which is a doctor, and ask the doctor, what is 2 plus 2? Doctor says 4. And you say, correct, how did you know it? Doctor says, I mugged it. So whatever works, we are good with that. Okay? So suppose we had rainfall, the original variable, or temperature, and then you fit a distribution to it. Then we are interested in finding out that magnitude of rainfall corresponding to which the probability of exceedance. So this is basically the quantiles. This magnitude corresponding to which the probability of exceedance, the area under this curve, is 1 upon 100. That would give me the 100-year rainfall, 100-year storm. Okay? This is how we do it. And therefore, not just so, instead of P equal to 1 upon 100, you can take 1 upon 2, 1 upon 5, 1 upon 10, and so on and so forth. So for different return periods, you can get the magnitudes of that variable. All right? How do we do that? We fit a statistical distribution to it. Now, it so happens that for certain variables, especially rainfall, the climate model's fidelity over the South Asian region is not great. For example, observational studies have showed that rainfall has declined over the last maybe 50 years of the last century. However, the models are telling, some models are telling it has increased, some models are telling it has decreased, etc. So in that case, instead of relying on climate models, we sort of try to estimate the counterfactual from observational data itself. How? Let's say I have 100 years of data. I'll assume the more recent climate, let's say 1950, 1960 onwards, as the actual world, and the early 1900s as the counterfactual world. Okay? So we sort of split the observational period, if it is long enough, into a sort of a prehistoric period, old historic period, which is counterfactual, and a more recent climate, which is factual. And then I'll look at the P0 and P1, the two probabilities in those two climates. And then how do we define extremes? So for defining extremes, there are two approaches. One is called the block maxima approach. The other is called the threshold exceedance approach. The block maxima is basically you have a set of values. Instead of looking all the values, you take the one which is in this block of values, whatever is the maxima. The most common example is you have daily values of temperature. Out of 365 values, you take the maximum value. So that's the annual maxima. Again, second year, 365 values, take the maximum. So you have a block of values, you take the maxima out of it. This is called block maxima. The alternate is a threshold exceedance approach where you fix a high threshold. The threshold has to be as high as possible, but not any higher. What do I mean by that? High, because it should represent extreme values. If it is too low, then everything will be above it, right? It has to be sufficiently high, but it cannot be so high that you have very little number of values left to fit that distribution. So the threshold choice is a little subjective, but let's say we have defined a threshold, then whatever values goes above the threshold, we call them as extremes. The block maxima approach is more common, so we are going to use the block maxima. Whatever discussion we'll have is applicable to the block maxima approach, and the distribution, don't worry about the equation. The distribution we fit is the generalized extreme value distribution. Everybody knows of the Gaussian distribution, the normal distribution here. How many parameters does it have? Mean and standard deviation. Okay, 2 parameters. Now, why I asked this question is the person, excellent professor who taught me statistics here in Bangalore, but not in ICTS, in IISc, was this statistician called Chiranjit Mukhopadhyay. I was taking his class and he was teaching us distribution, and he was telling that what is common to one field can be so uncommon to other fields. So he said he once he was approached by a biologist for collaboration, okay? The biologist say, hey, Chiranjit, I am fascinated with your techniques and I have a lot of data of bacterial growth. Would you like to use your models to study my bacteria data? And Chiranjit asks the biologist, oh, sure, I'd love to. Is your data normally distributed? And then the biologist says, of course it is normally distributed. Why would it be abnormally distributed? So I am assuming everybody knows what is Gaussian or normal distribution. It has two parameters. But this is the generalized extreme value distribution, which has not two but three parameters. And the third parameter is what is called the shape parameter, which is what makes this distribution very uniquely different from other type of distributions. It basically governs how the tail would behave. Okay. Now, once we have decided, we will stick to the GEV distribution. Now, the question is, how do you fit distributions? First of all, what do I understand by fitting a distribution or fitting any model to a data? It can be any model. It can be a y equal to mx plus c also. If I give you data of x, y pairs, ask you to fit y equal to mx plus c, what do you mean by fitting the model? By fitting the model, we understand estimating those parameters m and c. By fitting a Gaussian distribution to some data of random variable, what we are doing is we are estimating the mu and the sigma. Okay? Finding out the parameters is estimation or fitting the model. Okay? And once we have found out the parameters, we can test some hypothesis on it. But for today, we are going to stick to only estimation. The example I have given here is something that will be easier for all of us to perceive. We all know that Sachin used heavier bats. Okay? He liked using very heavy bats. So suppose the weight of his bat is the only parameter which governs the probability of his scores. Okay? If you know the weight of, what do I mean by parameter of the distribution? If you know the parameter, you know everything about the distribution. By everything, what do I mean? All probabilities. So if I know the weight of Sachin's bat, I'll know what is the probability of him scoring a duck. I don't want to know that, but I still can know that. What's the probability of Sachin scores a century? Yay, that's the probability I want, okay? Or between 50 and 100 and so on and so forth, right? So probability, all the probabilities will be known if the weight of his bat is known. So the weight of his bat is the parameter that we are trying to estimate, right? From what? I now have observations of what he had scored in each of the last 50 matches, let's say. So I take data of the random variable x1, x2, etc. x1 is the score in the first match, x2 is the score in the second match, and so on. From this, how do I estimate the weight of the bat? And the most popular approach of doing this is the method of maximum likelihood, which was proposed by this person who received knighthood, Sir Ronald Fisher. Either Oxford or Imperial or UCL, I forget which one, but somewhere in UK. And the method did not become very popular right away because there were certain asymptotic proofs which were later given by another statistician, Samuel Wilks. Once those proofs were given, the method of maximum likelihood slowly gathered popularity. By the way, Ronald Fisher had also links with India. Here is a photo of Ronald Fisher visiting an institute in India with two other Indian scientists, which you are going to tell me who they are. This is, I have heard Saha, I have heard Bose. Who's this? Yes, she's correct. How do you know? Oh, but I have had other people from West Bengal also who's not been able to identify, but thank you. Yes, you're right. This is Prashanto Chandra Mahalanobis. If you have heard of the Mahalanobis distance, like you have the Euclidean distance between 2 points, you can also have Mahalanobis distance. He is famous for other things too, but Mahalanobis distance is what people mostly relate with. And then we have Satyendranath Bose, after which the Higgs boson, the boson is named after him. I have had BTech students in my class who have heard of the boson, but not of Bose. Ironical as it is. And this is Ronald Fisher. So he was invited by Prashanto Chandra Mahalanobis. This building is ISI Calcutta, the Indian Statistical Institute in Calcutta anyway. And these two had done a lot of work on agricultural data sets in India. Okay, now coming back to the method of maximum likelihood, I don't know how far I'll be able to cover though. So we have we have a sample of Sachin's runs and we are trying to estimate what is the weight of his bat. What we do is we keep assuming different values of weights of his bat and find out what is the value of that weight which maximizes the probability of the sample that I have observed. This probability is called the likelihood function. Okay? Why? Let me try to convey the intuition behind it. Assume different values, 10 kg, 9 kg, 7 kg, 14 kg, 15 kg, 100 kg. For what value of the weight do I get the probability of Sachin scoring x1 is in the first match, x2 in the second match, x3 in the third match, etc. highest? Why would that give me the correct weight of the bat? Because this is what has happened in reality. You can't change that. This is the sample that you have observed. Now I'm going to go back and find out which value of the weight maximizes the chances of observing what I have observed. Okay, and then we make some simplifying assumptions, etc. We use the log likelihood function and then we differentiate. So basically maximize. For maximizing any function, we have to differentiate it, equate it to 0. So whatever value of theta maximizes L theta will give me the right theta. So with this maximum likelihood estimation, now I'm going back to my rainfall example and trying to fit the GEV distribution to the rainfall, annual maximum rainfall data, and maximizing the log likelihood function, which will give me the 3 parameters, mu, sigma, and xi. Once I have the 3 parameters, I'll be able to calculate what is the magnitude of xp corresponding to which p is 100. Or for a given x, what is the probability? Right? For a given x, what is the probability? So suppose in Kerala, in a day, there has been 300 millimeters of rainfall. I am now going to find out what is the probability of that 300 millimeters. Okay? And so this is a little more nuanced. I think I'm going to skip this. So I'm going to show you the results of what happened with the Kerala study. So this is the rainfall on July 30th in the whole of Kerala. And we defined a region in which the rainfall was the largest. This was also this includes the basin where the landslide had happened. And we see that say 300 mm had happened. Now we are going to look at return period versus magnitude of precipitation for the blue and the red. The blue represents the counterfactual and the red represents the factual. The horizontal is what we had observed, let's say 180 millimeters. This is the observed rainfall that happened, averaged over the entire region. 180 millimeter had happened. I'm going to see what is the return period of that event in the actual world and what is the return period of that event in the counterfactual world. And when you take the magnitudes of those two, the study concludes that roughly 10% the event has been made more intense. So for the same probability, the magnitude of rainfall in the actual vis-a-vis counterfactual is 10% more. Okay? This also sort of corroborates with the physical understanding that I told you, the Clausius-Clapeyron equation, per degree Celsius rise in temperature, 6 to 7% more moisture holding capacity, which eventually led to 10% increase in extreme rainfall. The pointer is not working. Okay. When we do it for temperature, similarly, so this is the region we had defined across South Asia, which includes India and Pakistan. And when we look at the magnitude, so the horizontal line is the magnitude of the maximum temperature. We look at the probabilities or the return periods in the counterfactual, the blue one, and the factual, which is the red one. And it shows, the results show that it has been made 1 degree Celsius hotter and 30 times more likely. So the chance of that event happening in a counterfactual world was 30 times lesser. All right. Now here I'm going to quickly change gear and talk about some unsupervised machine learning techniques for attribution. And the one that I'm talking about is what is called the EOF analysis, empirical orthogonal function analysis, or the principal component analysis. The procedure is the same. They have different, in fact, some studies, some books may also call it Karhunen-Loew decomposition. It is very closely associated with the singular value decomposition and so on. If you are a linear algebra geek, these are the different terms. But what we do in this analysis is that suppose I have two variables, x1 and x2. Okay, I want to reduce the dimension. So from 2, I can reduce it to 1. And I want that direction in which most of the variability. So most of the variability is lying along this direction, right? So I am going to find out a new direction, which is u1, along which most of the points lie. Okay. Suppose I have originally 3 dimensions instead of 2. So variable 1, 2, and 3. Here I see the maximum variation is along this direction. So that is my first PC, the first u1. Then the algorithm will also give me u2, which is orthogonal to the first u1. So u1, u2. Okay. So let us say we began with the random variable x, which was varying temporally and spatially. I want the new directions which are given by the empirical orthogonal functions and the new components along those directions, which are the u's. I'll give you an example which will make it a little clear. So all of you here are aware of the El Nino Southern Oscillation. This is a phenomena which happens in the Pacific Ocean, where you have anomalously warm waters in the coast of Chile and Peru in South America. Those people speak Spanish because the original tribes are no longer existing. Shayad battery khatam ho gaya. Okay, so Chile and Peru fishermen realize that every 5-10 years the waters become more warm than usual, and they called the more warm phase as the boy and the colder phase as the girl. So Niño is boy, Niña is female. Right. So during the El Nino Southern Oscillations, positive phase, which is the El Nino, we have warmer waters here, and it so happens that it is not restricted to the Pacific Ocean only. It can affect global weather patterns. Okay. Now, this is a process which is seen in the actual world, in a real physical, this is a real physical phenomena. But it is fascinating that if you look at the sea surface temperatures in this region roughly, and do that mathematical operation, we decompose x into u's and e's, then if you plot the e's, and this is from a class assignment of the postgraduate course that I teach, which Usman here had taken this course, he might have plotted the same plot. So if I plot the EOF1, the first EOF of the sea surface temperature data, I see a mode, a spatial pattern, which it looks exactly like the positive phase of ENSO. So it is quite fascinating that what you do mathematically to a data set can represent a physical phenomena. Similarly, in civil, is there any civil engineer here? Only Usman. So in civil engineering, there are, if you assume a column and if you keep applying load to it, the column will fail. The first mode of failure will be buckling like this. That's also quite fascinating that the physical mode of failure corresponds to something which you can mathematically derive. The eigenvalues that you derive from the stiffness matrix is exactly, the first eigenvalue will correspond to the buckling mode and so on. So with this concept, we wanted to apply the UF analysis. By the way, the UF analysis is pretty commonly used in climate science, and Shikha, who is one of the coordinators of this course, was among the first batch of students I taught at IIT Bombay. And she liked this correspondence between mathematics and physical real world phenomena so much that after the end of the course, she came and told me, at IITM, I have always used PCA without understanding what goes on behind it. And now I know the math behind it also. So what we do is we apply the UF analysis to temperature data. So this is average temperatures of Tmax, average maximum temperatures over the March-May season. And these are the trends, and the stippling basically denotes that the trends are increasing. Now we want to see what the EOFs of this temperature data shows us. So the first EOF is basically the largest mode of variability. This shows that this region here in the north central region has the largest amount of variability. So here you see the largest loadings. This again corresponds to the fact that there are other studies which have showed that in the real world, these are the regions where heat waves happen. The EOF2 is exactly the opposite of it. So this is called the dipole. And when we look at the corresponding principal components, which are basically the U's, then we see that there is a rising trend. So we decided to use this concept of, well, we didn't decide to use, we used it as a tool because it was serving as the right tool for addressing the question we were trying to address. The question we were trying to address is, temperatures over this region show a shift in roughly 1997-98. So the probability distribution shifts to the right significantly after 1998. And we tried to understand what can physically explain this process. To understand this, we looked at high winds. High up in the atmosphere, there are winds which are called jet streams. So we looked at wind speeds which are high up over this region, which are linked with heat waves in India. And using the EOF analysis, so we looked at the winds in this region, and we did an EOF analysis on those winds to define an index which we called as subtropical westerly jet index, and that shows a significant change roughly around 97-98. So this was eventually we linked them with different heat wave characteristics, but the moral of the story is that high up in the atmosphere, the winds are shifting northward, and we can use a mathematical machine learning tool such as the EOF analysis to define an index. And if we look at that index, we'll be able to link that index with the changes in heat wave characteristics over India. Okay, so this is the primary conclusion. So I'm going to stop here so that we have some time for Q&A.
Thank you, Professor Arpita. Let's thank her with, I think we have around 5 minutes at least for Q&A. So please raise your hand so that I know how many questions are around.
Hello, ma'am. I'm Bipin from IIT Kharagpur. So my question is, let us say I am doing an analysis of rainfall, causality effect of rainfall. I'm trying to predict rainfall using the oceanic climatic drivers. So after prediction, I'm trying to analyze what is the contribution of the drivers on the extreme rainfall events.
Okay.
So my question is, for defining extreme rainfall events, what technique should I consider? Block maxima value or threshold exceedance? Which will be better?
I wish I had a binary answer to this, but it's the same boring answer to many questions, which is it depends. So it depends on what you are really interested in. Typically, the block maxima approach works well because it is subjective. And we know that every year there will be some maxima which will affect, which will have some impact on lives and society. But so the threshold exceedance approach has a subjectivity around it, in the sense that how do you define the threshold? Should it be 90th percentile, 95th percentile, 85th percentile? There is subjectivity around that choice. That subjectivity is not there in the block maxima, so it happens to be a more popular approach. But you can also think of a situation where you did have a maxima, but the maxima was not extreme enough.
I consider ISMR.
So ISMR is average across the whole country and whole season, right? I would not look at ISMR if I am trying to study extremes.
If I am studying for ISMR, if I am predicting ISMR,
yes,
then for finding out the extreme of ISMR, which year it is extreme, then what?
I would not use the ISMR time series to define extremes at all. Because the moment you average over the season, the extremes are not extreme anymore. Everything has been averaged, right? Similarly, the moment you average over the whole country, the extremes are not extremes anymore. You have 2000 millimeter in Mumbai and 50 millimeter in Vidarbha.
Then you are not considering ISMR for extreme. I am predicting ISMR.
Then you predict ISMR, but don't predict extremes of ISMR.
Okay.
You predict the average seasonal rainfall using whatever techniques you can do. A lot of in principal component analysis has bhar ke applications in that. You can do PCA, you can do clustering, you can see what metrics work well. In fact, before the computer-based numerical weather prediction models, ISMR was predicted using a statistical model by the Met department.
Thank you.
Yeah.
Are there any other questions? Yeah.
Are there any online questions? I hope not. Yes. Good morning.
Thank you for that talk. My first question is more of a question on choice rather than grounded in fact. I noticed when you were talking about return periods, you chose to talk about increase in intensity rather than frequency.
Yes.
Like, is there any particular reason for that choice?
Yes and no. Yes, because intensity, so the magnitude of rainfall is what is most damaging. A 2000 millimeter rainfall vis-a-vis 100 millimeter rainfall, the 2000 millimeter rainfall will have more damages. But having said that though, so intensity is the first variable that we look at when you are looking at extreme characteristics. Having said that though, you might also be interested in finding out how many heavy rainfall spells am I getting and is that increasing over the years? All the concepts that I have talked about today are also applicable for that too, except that you cannot fit the same distribution. So there are theoretically justifiable distributions. So for example, if I'm interested in the frequency of events, how many heavy rainfall spells per year and whether that is increasing or not, for that my theoretically ideal distribution would be a Poisson distribution. And you can then look at what is the probability under the Poisson curve. Whatever concept I have talked about subsequently can be applicable to the Poisson model. The model will be different. Okay. Similarly, you can also look at the duration. How long is the heat spell? And whether that is increasing over the years. Right?
Thank you. That was for my first question. The second question, there was a plot in the previous slides, one on basically the natural world and the actual world. Yes, this one. So my question for this is, wouldn't the actual world future have a higher likelihood also? Why is it just a right shift?
So this is symbolic of the temperature. The temperatures are moving to the right because your average was earlier 35 degrees Celsius. Now the average is 37. So we have moved to the right. And in future, so we are already 1.5 degrees C above pre-industrial. In future, it's going to be even more. So the dotted one is actually the future one, which shifts even further right. So, but in certain situations, you may have, if I'm looking at droughts, for example, and climate change, I have not talked about droughts at all. We've done work on droughts too. In droughts, you can have the left extreme shifting more left.
No, my question
What
was,
is, yeah.
But between the actual world, present and future, there's no change in likelihood is what I'm asking.
Yes, there is change in likelihood, no? The area under the red dot for the same vertical line.
I'm sorry, am I reading this plot wrong? Because the right shift is for threshold, right?
No, the threshold is the same. We're looking at the same magnitude of the event. Let's say 35 degrees Celsius. Now I am going to look at the probability of 35 degrees Celsius under the green curve, which is only this much, right?
Okay.
That is counterfactual. Now the red one is today's climate. The probability has increased. It is this area. And then under the dotted curve, this whole thing is the probability under the dotted curve, which is the future probability. So it's even more.
Okay.
Does that solve your?
Yeah.
So by the time you pass on the mic, there are two questions. Do you want to take the online question?
There's no online question.
There's one.
There's one?
Think. Yes.
Okay. Would you sum in?
More than one now.
Given the uncertainty monsoon convection.
No, not this. Yeah.
Which one? The first one?
No, start from the bottom most, I think, and go up. Yeah, I think that is
This is the first one.
Yeah.
How changes in winds in higher troposphere have connection with surface changes in temperature? How have you established that connection? Do you want me to go to those slides? Okay, So this is what we have found, that there has been a regime shift in temperature. There has been a regime shift in winds also over this region. Okay. By the way, this Middle Eastern region has the highest rate of warming across the globe. So we see that between regime 1 and regime 2, there is a clear shift in the winds which are high up in the troposphere over that region. Now we defined this, the wind, we use the UF to define what is called the SWJ index. And then we fit a model between the SWJ index and the different heatwave characteristics. And from the model, we know how much percent of the variability, let's say I'm talking about heatwave frequency, then there is heatwave duration, and then there is cumulative heat, which is basically the intensity. So suppose for the frequency, I'm fitting a model between SWJ index and the heatwave frequency. Then the statistical model will give me how much fraction of the total variability in heatwave frequency is because of SWJ index, which happens to be 25%. This is how the link has been established. I hope I am able to answer.
There are two more actually online, so I thought those two.
But my preference is always to the in-person participants. So.
And then we stop.
So one second, the next talk is at 12 o'clock, right?
But there is a photo session in between and coffee in between.
So you can catch me in coffee?
Sure, that's I was thinking of
Yeah.
that. So maybe do you want to answer the online?
I'll answer the online.
So give two questions, three of you.
I'll talk to you during the break. Given the uncertainty in dynamic changes at regional scales, how effective do we find machine learning, especially unsupervised methods, in improving our understanding or attribution like heat waves? Okay, this is a philosophical question. How effective do we find machine learning, especially unsupervised? So unsupervised methods are almost always a precursor to supervised learning. So typically, the example I'll take, what's your name? Yeah. Dipayon. So Dipayon gave me an example where unsupervised learning will serve as a precursor to supervised learning. What is the unsupervised learning technique? He's going to use principal component analysis to get some modes of sea surface temperatures. That is the unsupervised learning part. But the supervised learning part is he's going to use those modes as predictors to predict the Indian summer monsoon rainfall. That is a predictand. So unsupervised learning by itself is not a solution to anything actually. It almost always serves as a precursor to a supervised learning. So that is what is the primary goal here, to predict something. And in order to predict something, I think there are my previous talk, the talk previous to me had talked at length about how machine learning can be integrated. Then there is a whole new branch called physics guided machine learning, which will be there in the afternoon today. So the importance and usability of machine learning for prediction is, I think, increasingly being established. So I don't know if I'm effectively answering the question, but unsupervised learning is not claimed in this lecture to be a one-stop solution. The second question is, would you some intuition why eigenvector basis capture this phenomena? What would a Fourier or a wavelet basis? Physical mechanism, wait 1 second, I'll come back to this. What would a Fourier or wavelet basis for decomposition capture? Would both of these techniques capture different interesting things? Yeah, you can use Fourier-based decomposition, you can use wavelets, you can use what is called an empirical mode decomposition. There are different decomposition techniques, but I think the principal component analysis is the most popular because it is very intuitive. It is telling you that if you have a data set of multiple variables, then and imagine so let's say 3 dimensions, then imagine a 3-dimensional space in which where is the direction of maximum variability. So it's that way it is very physically interpretable. That's why it is more popular. The wavelet or Fourier works well for time series analysis, not so much for the spatio-temporal patterns which we talked about. But yes, you can use those and you might get the same patterns or you might get slightly different interesting patterns. I have not done such a comparative analysis. Thank you for the answer, but still physical mechanism between the connection of SWJ to temperature is missing. Okay, I think what I can do is I'll share Tukaram, I'll share the link of the paper with you. It's in GRL, you can have a look at it. If you just write an email to me, I'll share the paper that has
So let us thank Professor Arpita
Thank you. Thank you.
for this nice talk.